Hey everyone! Today we're going to talk about Rotary Positional Embeddings, or RoPE for short, and how they're lying to us. So usually when people see this talk, the first question that they ask is RoPE in the room with us right now? And my answer is usually yes. If you're using any of these LLMs or you have their app on your phone, RoPE is probably in the room with you right now. Scary. But in order to understand why that's scary, let's go back in time all the way to 2013 and talk about what we did back then. So a long time ago, there were word embeddings that were called word2vec, and they had this nifty attribute of actually being embedding in a space that makes sense. At least in the sense that if you take the vector for king, subtract the vector for man, add the vector for woman, you'd get the vector for queen, or at least that would be the closest vector to the point that you'll reach. And that was a very cool attribute, and people were happy, and classifiers worked well using those embeddings. And it was very nice, though, it was the long time ago. Then in 2017, the transformer came and almost everything became awesome, and LLM started to be actually useful in real life, mostly thanks to the multi-head attention layer. And people didn't really care about the fact that the nice attribute of king minus man plus woman equals queen kind of got broken. In fact, it couldn't really even exist in the transformer architecture because if we take a sentence like, I like big dogs and you like small dogs, then the transformer will have an issue. And the issue will be that within the self-attention layers, the word small needs to attend to the second dogs, and the word big needs to attend to the first dogs. And the way that this issue is resolved is basically by positional encoding. And what positional encoding means is, well, let's add a small component to each word. This small component will be position dependent. And with that small position dependent component, we'll know which position is where and which position is closer to other positions. So if we look at the actual formulation for that, we have the embeddings for dog, and we have the sinusoid positional embedding, and essentially positions that are very close to each other will get values that are close to each other and get vectors added to them that are close to each other. So the vector that will add to the word big will be very similar to the vector that will add to the word dogs, thus allowing big to attend to dogs and dogs to attend to big in a pretty straightforward manner, because they have a component in their vector that is almost exactly shared. Whereas if we take a look at big and the second time we use the word dogs, which is far away from big, the component that is added to the second dogs is pretty different than the component that is added to big. So they will have a component that is not shared, and instead of increasing their similarity and their product, it will not increase it, thus making it harder for them to attend to each other. And the model can actually learn that the big refers to the first dog and small refers to the second dogs. Rotary positional embeddings took a kind of a different approach, where the sinusoid positional embedding said, well, we'll just make a small change and add a small vector that will help close word attend to one another. Rotary said, well, let's rotate vectors, and if two positions are close, their rotation will be close. So intuitively, it's a bit odder. I mean, how would that work? The way I tend to think about it is something like that. So let's say all nouns share a certain component in their vector, and all adjectives share a different component in their vector that indicates their adjectives. We can learn that given a certain angle between words that are adjective and words that are noun, we have an adjective that can affect the noun. So if we have two, like a noun adjective pair that is very close to each other, like literally one position after the other, then the rotation will not bring them too far apart. Whereas if we have big and the second word dogs, which are many positions apart, then the rotation will break that angle between the right angle that the model expects to see between a noun and its adjective, thus making us able to learn that small dogs is small acts on the second dogs, big acts on the first dogs, and it is something that becomes learnable, whereas without any positional embeddings it would be completely unlearnable because dogs and dogs have the same vector in the embedding matrix. Now, there is a point here, and the point here is that it completely doesn't matter. The only thing that actually does matter is where you add the positional embeddings. So in the original paper, we added the positional embeddings right after the embedding matrix. And it was great because the model could learn the difference between the first dogs and the small dogs, and the self-attention layers could actually work, but it had a side effect. And that side effect was that at the end of the transformer block, somewhere at the end of the model, we'll need to actually infer the original words. We need to be able to take the output vectors and project them onto the embedding matrix to get our cross entropy loss. So the model has that extra burden of, during its many layers, it needs to essentially reverse the entire addition of the positional embeddings. So it's not impossible. Obviously, the model does it, but it's an extra burden. It interferes with the learning process, and it does make sure that your embeddings are unable to capture nice spatial features like word-to-vec. Now, when we look at the Rotary Positional Embedding paper, they didn't do that. Sure, they had a different way to do embeddings, and you don't add the matrix, you multiply by a rotation matrix, and that's all fun and good. But the thing that contributes the entirety of the performance gain is the fact that you only apply it to Q and K on every layer of the model. So only on the keys and the queries, never on the values. You never destroy the embeddings themselves, because why would you? The only point of the embedding, of the positional embeddings, is to make sure that big can attend to the first dogs more easily and small can attend to the second dogs more easily, and there isn't any mix-up. But there is absolutely no reason to mess up V itself. There is no reason to change the embedding themselves. We just want to make sure the right words can attend to the words that they should attend to. So why not just ensure that? And in the Rotary Positional Embedding paper, they did, and it worked. But the problem is that the thing that worked is only mentioned here. No one talks about that. If you see that red circle, that is the only place where it is mentioned that they do not apply on V. There is a large chunk of saying, well, this cos, sine, minus sine is an actual rotation matrix, and there is an even larger chunk that says how we would apply this for a linear transformer. But the thing that actually gives the benefits is not mentioned at all. Honestly, it kind of feels like the purpose of this paper is to obfuscate the thing that actually improves the models. And I do get that if your paper was hey, why are we adding positional embedding to V where we should just add it to Q and K? That seems obvious. That would be a very short paper, might not get published, even though it will be just as good and even better in terms of the insight that it helps people get. But it is what it is, and that is where the benefits come from. So, obviously, the question that you might ask is, wait a second, how do you know that? And the answer is also pretty simple. Try it yourself. It's a very simple thing to take a vanilla transformer model, chop off the positional encoding, and just add them to Q and V on every layer. It's not difficult. It's also not difficult to try to add the rotary positional encoding directly on the input embeddings and not adding them in every layer and see what happens. And if you do try that, you see that the type of embeddings doesn't matter. If you add them to every Q and K on every layer, the model works better than if you add them to just the embedding itself. And while I don't have experience training large language models from scratch, I have quite a lot of experience with training smaller language models from scratch and actually making that experiment, and the loss goes down just the same, regardless if you're using rotary or sinusoidal. The only thing that actually matters is putting that into the right place. So that's that, and that was what rotary positional embeddings were trying to hide from you. See you all next time.